Unmute. Welcome everyone to the next in our series of ferrolectures, seminars on fundamental physics of ferroelectrics and related materials. And we're really excited today to have Sergey Prosandeev speak to us. I'll say a few words of introduction in a second. So I'm Ron Cohen. I'm at the Carnegie Institution for Science in Washington, D.C. Our lab is called the Earth and Planets Laboratory, but we do a lot of materials work and so forth too. And so we're really excited about this and are looking forward to this talk today. These lectures are generally going to be, and they have been, on the second Thursday of each month at 10 a.m. Eastern US time. And we'll continue these, though we're going to be on hiatus for these lectures until March because we have the workshop coming up at the beginning of February. So there won't be any of these in January or February, and then we'll pick up again in March. So Sergey, who's going to be speaking to us today, is at the University of Arkansas in the physics department. And he's going to talk today about hidden phases with neuromorphic responses and highly enhanced piezoelectricity in relaxor and antiferroelectric prototypes. So Sergey got his PhD in 1980 in Rostov State University in the USSR, and he came to the US in 2000 and was at NIST and then came to Arkansas and has been working with Laurent Belèche since 2005 there, and he's done a very large range of really exciting works, a lot of them on what we could call classic ferroelectrics, a lot of work with experimentalists as well as first principles theory, along with experimentalists and without, trying to understand properties of important materials like doped barium titanate and PMN and bismuth ferrite and many other important materials. And he's also done a lot of work on, let's say, really novel ideas about complex polarization patterns in materials and toroidal moments, and a lot of really exciting new material things. And he's going to talk about some of that today. Let's see, there was something else I wanted to say. I'm not remembering what it was. So, oh yes. So please hold your questions. You can type them in the Q&A box actually during the talk, but you won't get an answer until afterwards. And at the end of the lecture, we'll have time for Sergey to address your questions. So please, think of your questions, and you can even type them in during the talk if you would like. And if someone has some kind of discussion they would like to add, we can even promote you to speak if you have something that you can't really just say in a sentence or two. Okay, so with that, I'm going to turn it over to Sergey. And so Sergey, you can go ahead and share your screen now, and I'm going to stop sharing.
Thank you, Ron. Okay, let me share. I still cannot start screen share because it is shared by.
Oh, I stopped mine. Let's see. Let's make sure that you have the sharing privilege there.
Mm-hmm.
You should be able to share your screen.
Okay. Thank you. Okay, so let me start.
Sorry, can you make that full screen? Your slide.
I did it. It is full screen.
For the display slide itself, no, it's just showing up as a small slide. So There should be a button for, I see it on the right there, the thing that looks like a full screen.
What I see, it is full screen.
Hmm.
Do you have two monitors, Sergey? If so, you might be sharing the wrong side.
Let me see. It is monitor 1 now, and let me see, show only on 1. So it should be.
There's a button in the bottom right of your display there that shows a little slide screen. Right to the left of the 110%.
So what can I do?
Push that button that's right to the left of the 110%. You had it working before when we did the test. Yeah. So there should be a full screen. Yeah, right there. Can you push that button on your screen?
100.
Yeah, click on that thing that. I don't think we can do it for you. You have to make your slide full screen somehow. I mean, we can live this way if we have to, but you had it up before.
Okay, let me start again.
If necessary, I can show them.
Do you see full screen?
We don't see anything right now, but we see you.
It is not shared yet. Okay, let me share it.
Yay! Okay. It's all yours.
Okay. Sorry for this trouble, and let me start from the team which participated in this work. So this is a collaboration of 3 universities and 2 from US and 1 from Paris. Sponsors are shown at the bottom. So let me start from brief introduction to the topic, and then I will talk a little bit about effective Hamiltonian modeling of the electric pulses. And the examples will be lead magnesium niobate, PMN, and sodium niobate, NNO. So results of the calculations then I will show during these pulses and after these pulses, and I will then also talk about results of elastic band modeling, which allows to calculate the best energy pass between different phases. And this will clarify some points. And finally, some analytical model will be presented. So electric pulse, what is it? So you see this example of an electric pulse. Time is in femtoseconds, and the length of this pulse in this picture is about 200 femtoseconds. So this is a really short electric pulse, and we are interested in how this pulse influences the ground state of ferroelectrics, antiferroelectrics, and relaxors. So as introduction, let me first show maybe one of the first papers which was experimental. And the dashed line is the electric pulse, and the solid line is the displacements of the atoms in strontium titanate thin films And time is in picoseconds. So first you see that the displacement curve is shifted with respect to the electric signal curve, and also so it is wider than the electric pulse. The authors of this paper, first author is Katayama, suggested that this behavior stems from anharmonicity. And you see that in the equation of motion, they added anharmonic terms, these last two terms, and they think that this fact that the displacement do not follow the electric signal, but they have some delay time, this follows from the anharmonicity. Actually, I disagree with this, and I will talk about this later. Another paper, first author is Lee in Science, and this is two slides are experimental. So the first slide shows birefringence, and what is attractive after the pulse, this sharp peak, after the pulse, there appear these oscillations of the birefringence. So the authors say that phonons are excited by this pulse. Again, in our point of view, this looks different, but again, I will talk about this later. And the second slide shows the second harmonic. After the electric pulse, and we see that at low temperatures, so 5 Kelvin is the blue curve, which is the widest. So the lower is temperature, the wider is the response of the second harmonic. And also we see oscillations of second harmonic, which are probably due to phonon excitations, like in the first slide. And the lower is temperature, we have the response thinner and thinner, and finally at 60 K, we already do not see strong oscillations after the pulse, and the response is rather thin. The last slide shows calculations from done in the Andrew Rappe group, and you see dashed line is the electric signal, so the pulse which they model by using Gaussian function, and the red line is the local mode response, which is, like I said in experiment, is wider than the electric signal. And so it is decaying slowly from some large values. So the authors say that there are hidden states which are probed by this electric pulse, and we occupy these hidden states in the way from the ferroelectric state at the maximum to a paraelectric one or quantum paraelectric one at larger times. Again, so our point of view is a little bit different, while we also talk about hidden states. So I will show what is different later. Here we see also oscillations at the bottom of some antiferrodistortive order parameter after the pulse. So this is also an interesting feature, that the electric pulse excites not only polar phonons, but there are other oscillations related to non-polar modes. So one more paper. This is the first author is Boyne. So this is about tunnel junction made from BFO sandwiched between metals, and you see that this author in the first slide at the left, they observed memoristic effect, which means that resistivity has different hysteresis loop depending on the maximum voltage reached applied to this sandwich. So the lower is voltage, maximum voltage, and we have smaller loop. And the author said that we can make the system to learn from some electric pulses, and they apply electric pulse and two electric pulses in sequence, and the response at the bottom is shown for some quantity related to response of the atoms, depending on whether these two pulses are in phase or anti-phase or have a different shape. So these authors make some relation of this experiment to so-called synapse behavior in our brain. So synapse is such a thing which is placed in between two neurons. So you see here pre-neuron and post-neuron, and the author said that if we apply to pre-neuron some pulse, electric pulse, and to post-neuron another pulse but shifted, then we can have some complex response from the synapse due to these two pulses. And the pictures above obtained from BFO just illustrate this difference, that we can make synapse to learn from these pulses. So this is interesting relation of ferroelectric system to neuromorphic system. So this is also, I will talk about later about this proximity. So final paper which I want to show in introduction is a paper introducing a model which is called leak integration fire model for neurons. So in this model, they have three neurons at the left passing electric signal to the fourth neuron, and the fourth neuron integrates or collects and then somehow treats these pulses, and the function of the voltage versus time is shown in the middle. So we have different signals, and they suggest that only the signals which have height above some threshold, these only signals can go through the fourth neuron, and this model, this is just because of this model is called Elec integrator fire model, because all other signals, they go to the ground, and only the maximal signal goes through. So this model belongs to so-called neuromorphic behavior, which are studied by biologists. And what is neuromorphic? This means that we have first some signals, maybe several signals, maybe from several neurons, and these signals reach synapse, and synapse integrates these signals into one result, and the function which it uses for the integration depends on the features of these pulses. So after this integrated signal reaches some value above threshold, we have fire. Fire means that the signal goes through the next neuron, and then it goes to some neurons which make some real work, like, you know, movement of the body, etc. So now let me start just the bulk of this report, which is about calculations of this response to these electric pulses. And we use effective Hamiltonian method, which was introduced first in these two papers, and then I should say that this model considers a limited number of the degrees of freedom, and specifically these are local modes which are proportional to local dipoles. In homogeneous strain and homogeneous strain. So our first example is lead magnesium niobate, PMN, which is a relaxor, and effective Hamiltonian for this material was created by in Arkansas group, and so this is the reference. So I should say that local mode in this Hamiltonian is centered on lead ions, and it includes random fields on lead ions stemming from the surrounding niobium and magnesium ions. And this field is random because niobium and magnesium are randomly distributed in their sublattice, and they have different charges. So just a few words about PMN. It has very large value of the dielectric constant at room temperature and a little bit below. And this response, dielectric response, strongly depends on frequency. Effective Hamiltonian calculations showed that it is possible by using those random fields which I told you about to get this wide curve of the dielectric permittivity versus temperature, and inverse temperature behaves like an experiment. So, for example, at high temperatures, behavior is linear. And then it deviates from the linear behavior below room temperature. And we have first specific temperature, Burns temperature, which shows the point where this straight line start declining from straight behavior, and T naught or T star just extrapolated position of the temperature corresponding to this straight line. Okay, let me just switch to the electric pulses in PMN. We used in this calculation the product of Gaussian function and cosine, and parameters are shown here. So we applied this pulse to PMN to see the response. And this is the result for one pulse. We see that after one pulse, the polarization first gets some large value and then is decaying and oscillating. So it reminds the study on strontium titanate I showed before. So this behavior is normal. But let me proceed with a train of pulses. So now we have a few pulses with some distance between them, and they just are applied in sequence. So what we see, the polarization is increasing after these pulses, and each pulse increases this polarization by some value, and this part we call integration part, until we have saturation where the polarization is maximum. So it is very interesting to understand, are these intermediate states stable or metastable? Like, for example, we know that this ferroelectric phase at the top, it is definitely stable. And to answer this question, we did calculations after 4, 8, 12, 16, etc. picoseconds by switching the electric field off, and we see that polarization stays constant, more or less, of course, constant. So, for example, here it drops a little bit, but in other cases it stays longer in this constant at constant value. So this is what we call hidden states. You see the difference? These are not intermediate states which appear dynamically, but rather these are states which actually in our calculations with bias fields, we could not reach them. We had a jump from a relaxor state under the field, I mean bias field, to the ferroelectric phase without any intermediate state. But here, by using these pulses, we can see these intermediate states having intermediate values of the polarization. Also, we calculated the dielectric constant and found it very large compared to the limiting, compared to the values in the limiting phases. So these hidden states are definitely peculiar and have very interesting properties. So they should be studied also more in the future. This plot shows how to measure the occupation of different states, and we suggest using the percolation strength, which is the number of the ferroelectric ions in the connected cluster. And connected cluster is the cluster which spreads from one boundary of the supercell to the opposite boundary, and in this cluster all dipoles are approximately they look in the same direction. So we see that the percolation strength approximately linearly increases and then saturates when we reach the ferroelectric phase. So we tried also asymmetric pulses, and the result is the same in the sense that we had intermediate states after each pulse. These states are different. We also tried experimentally designed electric pulse, which was supplied by Dr. Talbayev to us, our co-author. And this pulse is interesting because it has zero integral. And again, we found with this pulse, this intermediate hidden states. After each pulse, we have different state. So I also want to say that this microstructure, just during the pulse, before the pulse, and after the pulse, is different. So the polar nanoregions, they change during this pulse and after this pulse. So we have a strongly inhomogeneous response of the matter to these electric pulses in PMN, in relaxors. Now I want to switch to sodium niobate. So sodium niobate is probably the most complex antiferroelectric known, and it has very many phases, antiferroelectric phases and ferroelectric phases. So this is a very complex material, and I show here in this slide the modes which are common for sodium niobate. These modes can be polar, like first two, antipolar, like second two, and antiferrodistortive, like the modes at the bottom. The Q points X, delta, T, R are shown in this at the bottom right, and you see that, for example, delta antiferroelectric mode is the middle between gamma and X points, or T is the middle between R and M points. So you see that the structural modes and antiferroelectric modes are very, very complex in this material. So effective Hamiltonian was made in this citation in 2018, and up to 5 phases were found with this Hamiltonian, including very complex twin phases, which has twins, local twins, which do not have periodicity. So electric pulse we used in this matter is shown in this slide, and we studied also how the system responds to this pulse. Here you see the application of this pulse to PCA-to-1 phase, which is partially ferroelectric and partially antiferroelectric. So you see that after one pulse, we have response which is wider than this pulse, and they appear low frequency and high frequency oscillations. Besides this polar mode, we see that antiferrodistortive modes also respond to these pulses, like it was shown earlier for strontium titanate. And antiferroelectric modes also have some spike and then decay after this pulse. So the train of pulses in sodium niobate, like in PMN, also results in the hidden states, which have intermediate value of the polarization of antiferrodistortive parameter and antiferroelectric parameters. In NNO, we also, like in PMN, found the memristor effect. So these lines show the result after some time intervals, and we switched the electric field off, and you see that polar mode remain constant in this case after we switch the electric field off. And the same is true for antiferrodistortive parameters and antiferroelectric parameters. So we see that actually these phenomena are rather general, because we see that not only relaxors but also antiferroelectrics, they have these hidden states. To study these hidden states, we calculated the piezoelectric coefficients and found them extremely large. They are much larger than the coefficients in limiting phases. This is another development. Here we used elastic band method and applied it to the effective Hamiltonian method. So we were able to find the path between PCA-to-1 phase and R3C phase. The intermediate states have PC symmetry. And you see that in this path, this is energy versus the image number in the sequence from PCA-to-1 to R3C phase. So we see that there are some small wells in the path from one phase to the other phase. And these hidden states are exactly the same, at least polarization is the same as we found those states we found in the during the train of the electric pulses. We did also calculation within WASP by implemented in WASP elastic band method. And we also found in the path between these two phases you see some wells or inflection points which show that even first principles show the presence of the intermediate hidden states which are not seen in experiments with bias field. And at the bottom you see the plot how the modes, structural modes and polar modes change during this path. So we see that intermediate states have some intermediate values of these parameters. So the model we use to understand these results is just a harmonic oscillator forced by external force. So this model is of course minimal, and this model cannot explain those hidden states because the hidden states are due to phase transitions. But here, by applying this model, I want to show that we already in this model have oscillations after the pulse, and we have wider response compared to the beats of the electric pulse. So these are general solutions and specific solutions of this differential equation. So I don't want to talk about this derivation, but the point is that they can be found analytically, and we actually fitted this model to our results, and these results we will submit later. So I want to show now only qualitative features of this model. So at the top we see shape of some electric pulse, and we have two possible responses of the system. One is for the underdamped case, when the for example, local mode oscillates after the pulse, and because of damping, it diminishes toward higher times. And overdamped case, when the local mode decays after the pulse. And this, the beats of the response depends only on the susceptibility of the system. So, okay, let me just show the conclusions that we found that two matters which we considered have memoristic effect, have hidden states, and so these hidden states are seen from the calculations of the response to the electric train of the electric pulses, and in the energy path between different phases. We also found that dielectric and piezoelectric properties are enhanced in these hidden states, and also we qualitatively explained the excitation of the phonons within just harmonic oscillator model. So this is my acknowledgement, and thank you very much.
Okay, thank you. That's great. Thanks a lot. So you can leave your slides up in case someone has a question on the slides. Let me see what people have typed in here. So there's a question. It says Jan Deck. I'm not sure if that's January, December, or if that's a person's name. I think it must be Jan Deck, right? It says, does it mean that you're approaching the so-called intelligent materials defined by Newham, more advanced and smart materials? I don't know what you're going to say about this, but that's a question for you.
We did not think about this at this angle, but okay, this is good. This is a good idea. I should read that Newman papers about that to answer this.
Right. I have a lot of questions, but let me, I want to give people a chance first that typed in. So Ruben Kachachurian asks, you show polar regions after the pulses. At which moment do they stabilize? Is it related to the size of the clusters, or is a specific shape needed? I'm not sure if he's talking about specific shape of the polar regions or of the crystal, but maybe you understand exactly the question. When do the polar regions stabilize after the pulses?
So after the pulses, we first in PMN we see the increase of the polarization, which remains whether stable or metastable. I cannot answer if it is stable or metastable because our time interval studied, you know, these are hundreds picoseconds, but within these hundreds picoseconds, it is stable, these hidden states, and they have enhanced value of the polarization. So microscopic structure shows that, okay, the dipoles more or less homogeneously are oriented along the field, and this contributes first of all to the connected cluster. But free clusters, smaller clusters, they just maybe reorient. And actually, this point we studied in our recent work on switching of the polarization in ferroelectric mode of PMN. And there we discussed our results from the point of view of percolation theory. So better to look at that paper, and it gives full answers to this question.
Okay, so let me ask a little. So we had a question. I'm not sure if Professor Kamba wanted to speak on camera or if he wanted to type it in. But let me go ahead first because I haven't heard back from him. So we showed some time ago that, like in pure PMN, there's actually a ferroelectric ground state, and it just doesn't form because it's just on growth, it's just hard to get it to form. But if we, at least in simulations, if we apply even a static electric field, then we get a polar state. And we did some MD simulations as a function of both temperature and electric field, and actually mapped out a phase diagram for that. So what you're calling a hidden state, I mean, what's different about that than just the fact that that you have a metastable state, like a apparently disordered relaxor, whereas it really should the most stable state would be ordered, but it just doesn't form spontaneously unless you, say, pull the sample or something like this. Is there something different about what you're calling a hidden state?
This is an integral characteristic which we suggested, this strength of the connected cluster. So there is a cluster connecting one border of the supercell with the opposite border. And this cluster gets more and more ions in it when we go from the lower hidden states in my picture to higher hidden states. So this is just the growth of the connected cluster, first of all, which, if you look by eyes at the picture, actually you do not see it. This is a matter of treatment of the results, which allows us to calculate the strengths of these clusters. So because it is very wavy way how the dipoles can contribute to this cluster. When we take one dipole, nearest dipoles can look in different directions, but one of them can be in the same direction. So this connected cluster spreads in this last direction, etc., etc. So the net which is attributed to the connected cluster is actually rather as I said, wavy, and by looking at the snapshots, there is no chance to see it. This is a result of mathematical treatment only.
Do you have a slide to show or to explain what you were just saying, or might be a little clearer?
This is the strength of the connected cluster, and you see that, so we see that it is definitely increasing in size during time, and time corresponds to more and more number of the electric pulses. But let me see where is the microscopic picture. In this picture, you see this is polar nanoregions in one plane.
I see. So you're saying you're not seeing a bulk ferroelectric state. You're seeing a reconfiguration of the polar regions.
Absolutely, because for example, if we take this polar nanoregion, then we should look also in the upper and in the other planes. It can go through other planes to proceed. So from this picture, we definitely see that connected cluster does exist, and it is increasing in size. But from look at the one plane, we don't see this.
Yeah, I see what you're saying. Okay, very interesting. So I don't want to monopolize things here. So we have Stanislav Kamba. Can you turn on your can you unmute yourself and turn on your camera, and you can discuss?
Hi, Sergey. Nice talk. I wanted to ask you, your electric field is practically terahertz radiation. And so it must be somehow in resonance with the ferrotic soft mode. Doesn't matter whether is it in PMN, NNO, or at the beginning you mentioned as well, and in STO. In STO, in strontium titanate, this paper in Science shows that this effect is strong only if it is in resonance in this soft phonon, and if it is pumped at higher temperatures, when the terahertz radiation is out of soft phonon, then this effect is not seen. So my question is, what is the difference of your hidden phase and field-induced ferrotic phase in strontium titanate or in PMN?
You can say that in that paper, you see that the polarization is decaying after. You see that it is decaying and diminishes after the pulse. So it doesn't exist, this intermediate hidden state doesn't exist, say, after 20 picosecond.
Yeah.
Here also we see it is constantly decaying. And decay is can be shown just in the harmonic oscillator model. So this is not...
Excite the lattice, you change the structure in picosecond time scale, and then it decays and it goes again in parallel state. they claim that they have a ferroelectric state because they see second harmonic generation. There are induced.
Right. This is field-induced second harmonic. This is not, own second harmonic. But field-induced second harmonic, this is not, this is...
Expect that if you will have in strontium titanate, let's say, train of pulses, that you will finally stabilize this hidden phase, like in PMN, you calculated?
My personal opinion is the following. If we have first order phase transition between two phases, like in PMN, relaxor and ferroelectric, then and only then we can have intermediate hidden states, and you can relate this also to water and vapor coexistence. So we have phase diagram where they can coexist, and the coexistence depends only on the pressure, on the volume. But in our case, we apply, like in memristors, we apply some limited number of the pulses, and we are not in the ferroelectric phase and not in the relaxor phase, but somewhere in between. And in one paper, where was it? It was said that this is because of incomplete switching. You see the point?
Yeah. So that's great. So I think we should thank Sergey at this point. I think this is really exciting. It's like going to a talk at the very beginning of the design of digital circuits or something like that. So I mean, I think that this is going to grow. Let me just ask a last very quick question. I mean, do you basically need a nonlinear material, I guess, for this behavior to exist? Is it required that it be a relaxor or a ferroelectric, or I guess those are just prototypical materials where one should see strongly nonlinear dielectric response?
This depends on what we want to have. For example, in this plot, you see the response in strontium titanate at low temperatures. And okay, the response is wider. The response can have oscillations after after the signal. If we want these features, this can be done on, I think, any material, actually. But closer to phase transitions, we have a larger susceptibility of the system, and correspondingly, this response will be wider, at least. But what I told about was a little bit different. Hidden states in our calculations are intermediate states between two phases. So this there is no decay back to the initial state. But we can return the system back, for example, by heating the system and then cooling down. Closer to the phase transitions, we can have this phase transition, but partially.
I don't want to break my own rules and go over the hour, but let me just real quickly, I mean, it seems that's a critical thing, is this being able to return it to the initial state if you want to have something that works over and over again. So is there any other way is it possible that could be done electrically rather than by heating? Is there any possibility some series of pulses, maybe of opposite polarity or something, could turn it back to the original state?
I haven't heard about such experimental studies. We collaborate with experimenters on this matter, and they started some new experiments, but they are not done yet, as I know.
Okay. I really, everybody, I thank Sergey again. I really appreciate it. Let me just quickly wrap things up. Let me, if you stop sharing, I want to share just some final closing slides. That was fantastic. I really appreciate it, and everybody does, I think. Where did my slides go? Sorry, I have too many windows. Here we go. Okay, so thanks again to Sergey. We have had a series of these so far. If you the previous talks are all on YouTube, and I think the easiest way to find them right now is if you go onto YouTube and just search for ferrolectures, you'll find them on there as a playlist. So this talk and the previous talks are available for you to look at again, and we will pick up these again in March. Though I still have to, we still have to come up with a schedule for next year. I want to mention we are having the Ferro 2022 workshop, Fundamental Physics of Ferroelectrics and Related Materials, will be February 6th to 9th, 2022. It's already, registration is over for presenting, but if you wanted to just participate virtually by viewing, or even we have some slots on site if you wanted to come without and say just bring a poster or something like this. It's still possible to go to the website here and register, and we have over 100 people registered, so it looks like it's going to be an exciting meeting, and I want to thank everybody for their help and participation in that. And so with that, I think we're at the end of the hour, and we're going to close the session, and we'll pick up again in March with the next one of these, and in between the ferroelectrics workshop. So thank you all, and have a good New Year and holidays, and keep healthy.